Hello everyone, myself V Dinesh and my roll number is 536 and my topic is graph signal processing for machine learning, a review and new perspectives. We live in a connected society. Data collected from large scale interactive systems such as biological, social and financial networks become largely available. GSP for exploiting data structure. GSP typically permits to model, analyze and process data supported on graphs. Consider weighted and undirected one graph G is equal to V comma epsilon with the node set V of cardinality n and edge set epsilon. A graph signal is defined as a function x maps x maps from V to R that assigns a scalar to value to each node. The main research effort in GSP is therefore concerned with the generalization of classical signal processing concepts and tools to graph signals. One key development is that the set of eight vectors of the graph Laplacian matrix or a graph shift operator, a generic matrix representation of the graph, provides a notion of frequency on graphs and helps define the so-called graph Fourier transform GFT. For example, consider a combinatorial graph Laplacian L equal to d, d minus w, where w is the weighted adjacency matrix of the graph and d is degree matrix. GSP-based ideas thus provide new tools for exploiting data structure and relational priors. Since their inception, they have been applied in the context of a wide range of machine learning problems. Regression is one of the basic forms of supervised learning, where, in its simplest setting, we are interested in learning a mapping from a set of inputs or features to a real value output or response. GSP provides an interesting alternative to tackling such regression problem by assuming that observations of the responsive variables from graph signals with certain properties, the example smoothness on a predefined graph. Graph-based classification. Another basic form of supervised learning is classification, which is similar to regression but with a categorical response variable. Recent advances in deep learning, in particular convolutional neural networks (CNNs), have led to significant improvements in tasks such as image classification. JSP provides a convenient tool to address such challenge. More specifically, by providing a notion of frequency and a GFT, convolution may be implicitly defined via the graph spectrum domain. In particular, the convolutional filter defined in graph spectral domain is not necessarily localized in the spatial spatial node domain, a property that is often decided in a neural network design. Furthermore, the necessity for computing the 8n composition with a complexity of order of n cube as well as the GFT via the matrix vector multiplication with a complexity of order of n square prevents this framework to be applied to large scale graphs. Graph based graph based clustering and dimensionality reduction. Unsupervised learning is another major paradigm in machine learning, where clustering and dimensionality reduction are two main problems of interest. Graph-based clustering, in its simplest form, aims to partition the node set into mutually exclusive clusters using a similarity graph. While classical solutions are usually based on generalization of concepts such as modularity to a multi-scale scenario, multi-scale transforms in signal processing such as wavelet transform provide a natural alternative. A simple hierarchical clustering is then applied to a similarity matrix at different scales to obtain multi-scale clustering. In the context of graph structured data, this usually means learning a low-dimensional representation for the data entities in the presence of a graph that captures the pairwise similarity between them. Classical solutions to dimensionality Classical solutions to dimensionality reduction, such as matrix factorization and autoencoders, have recently been combined with advances in GNNs to provide novel solutions. GSP for improving efficiency and robustness. Although GSP is a framework originally developed for incorporating the graph structure into data analysis, since recently Many classical machine learning algorithms have also benefited from exploiting typical GSP tools. Significant improvement in terms of robustness with respect to scarce and noisy training data or adversarial examples have been shown in tasks such as semi-supervised learning, few-shot learning, zero-shot learning, and multitask learning. Furthermore, large-scale data analysis and statistical learning can benefit from typical GSP operations such as sampling and filtering to reduce the computational complexity and time of graph-based learning. Regularization has been introduced in many learning architectures, including DNNs, in order to improve the performance of supervised and semi-supervised learning tasks. In semi-supervised settings, the last term has been augmented by a graph-based penalization term that biases the network towards learning similar representations for neighboring nodes on a graph that contains as nodes both labeled and unlabeled data. The overall goal is for each task to interfere to infer the parameter vector that optimizes differentiable cost function. Looking at the cost function as a signal on the graph, the knowledge from other tasks can be exploited by imposing a regularizer on the task graph, promoting the existing relationships between the tasks. This work shows how the structure between tasks can be inferred and exploited in learning to learn or meta learning settings, generalizing the learning process across tasks. In addition to robustness in terms of data samples, another natural consideration is the stability and robustness of graph based models against topological noise. In addition to stability results above, there exist several other studies on the impact of perturbation or uncertainty in the graph topology on GSP and network analysis in general. The benefit of graph priors in machine learning tools in terms of data efficiency, robustness, and generalization has been empirical and theoretically supported. Nevertheless, these learning frameworks usually scale poorly with number of graph nodes, resulting in high computational complexity in large-scale problems. A Cartesian product graph can be used to modularize a regular grid image in order to gain in terms of computational efficiency in the computation of agent decomposition for GFT. This enables efficient implementation of GSP analysis on large graphs via parallelization and vectorization. Analysis of complex systems typically involves large sets of data whose underlying structure is often unknown. Such structure can be estimated from the data in order to permit effective understanding or visualization of the system behavior. More recently, the problem has been addressed from a GSP perspective, where the structure is modeled as a graph that is to be inferred by exploiting the interplay between the graph and the signals observed on the nodes. Graph-based graph learning frameworks therefore have the unique advantage of enforcing certain desirable representation of the signals via frequency domain analysis and filtering operations on graphs. A first attempt to exploit GSP tools in order to better understand complex learning architecture is the framework proposed called margin. The central layer of margin is then to use GSP to identify fluctuations of the signal on the graph, which serves as explanation. In particular, high pass graph filtering reveals which, which nodes can maximally describe the variations in the label agreement signal. The node influences the node influence scores are computed as the magnitude of the filter signal value to at that node. On one hand, GSP provides a new theoretical framework for incorporating complex structure within the data and contributes to the development of new data analysis and machine learning frameworks and systems. Furthermore, GSP tools have been utilized to improve existing machine learning models, mainly in terms of data and computation efficiency, robustness against noise in data, graph structure, and model interpretability. On the other hand, machine learning problems such as classification, clustering, and reinforcement learning, as well as their application level in real-world scenarios, also provide important motivations for new theoretical development in GSP. That's it. Thank you, everyone.